Welcome to part 3 in our discussion of probability tables and relative risk. For part 3, we will talk about the idea of conditional probability, as well as the idea of relative risk, which is a measure of association between two binary categorical variable that you have. So for example, one variable might be an exposure, the other variable might be some outcome. And relative risk is a measure of association for these two kinds of categorical variables. You see it a lot in biology, public health, epidemiology, but also psychology, sociology, and economics. The idea is that you're conditioning on some exposure and you're looking at some outcome variable. The exposure might be something like secondhand smoke, but also an exposure might be some sociological conditions such as living in extreme poverty. And before we really look at relative risk, we should talk about what it means to have some kind of conditional probability and how that's different from an unconditional probability. The reason is that relative risk as a measure of association is built on conditioning, on conditional probabilities. So what is unconditional probability? We've been working with unconditional probabilities so far. So that's just expressed in this notation. You have some event A, and you give that an overall probability. So there's some event of interest, and we just use this kind of notation. An unconditional probability, it's sometimes called a marginal probability. Sometimes you will see unconditional probabilities, and these are just given in the 2x2 table. So here we have our 2x2 table for whether or not a respondent is poor or not poor, and whether the respondent has health insurance or does not have health insurance. The unconditional or marginal probabilities are simply given in the margins. These are equivalent conceptually to the unconditional proportions and percentages that we've discussed in previous lectures. A conditional probability, the idea is that we're conditioning on some other event when we calculate our event of interest. We encounter conditional probabilities all the time, and many questions of interest are in fact based on conditional probabilities. A conditional probability, what it really asks is, given that we know B happened, what is the chance or probability that event A happens? So we see this all the time. If you're overweight, what is the chance that you'll have diabetes? Given B, what is the probability of A? If a child grows up in a poor neighborhood, so that's the conditioning event, what's the chance of developing a mental health problem? That's our event of interest. What is the chance of developing breast cancer given a woman has a particular genetic marker? Many, many questions of great interest in the social sciences and humanities entail conditional statements just like this. Whenever you see some kind of phrase or question of interest, you know that you are encountering some conditioning when you see the words if or given. So given B happened, what's the chance A happens? If B happens, what's the chance A happens? These are all ways of stating conditional probabilities. Another point about conditional probabilities is that it's very important to pay attention to what you're conditioning on, if you're conditioning on anything at all. So let's look at these three sort of statements. They are different but similar. If a woman has breast cancer, the probability she will test positive on a screening test is 90%. All right, so in this case, we're conditioning on the event B, breast cancer, and then we're calculating the probability of testing positive. So given breast cancer, what's the probability of testing positive? If a woman tests positive on a screening test, the probability that she will have breast cancer is 90%. So in this case, we are conditioning on a different event. Instead of conditioning on whether or not a woman has breast cancer, we're conditioning on whether a woman tests positive on a screening test. And then we're finding the probability of having breast cancer. So for the second statement, you can say, given A, testing positive on a screening test, what's the probability of B having breast cancer? And then this last statement is the probability that a woman has breast cancer and tests positive on a screening test is 90%. So the last statement is in fact not a conditional probability, it's a joint probability. It says given A and B, what's the probability? Each of these three statements are different. The first two statements are conditional probabilities, and the last statement is a joint probability. They are not the same thing, and they will give you different results and different answers. And these kinds of questions were in fact posed to doctors, and most of them messed up. They screwed up the actual interpretation of these statements. So be very careful about what you're conditioning on, if you're conditioning on any event at all. So how do we write out what a conditional probability is? So we write out a conditional probability in this way. A is our event of interest, and then that vertical line, that tells us, you can read it as given or if. And then B is our conditioning event. So we would read this as the probability of A given or conditional upon B. To put it another way, this tells us the probability of A if we condition on B. One important point is that you can think of this kind of statement as subsetting to that realm of the space in which event B occurs. Right? So we're just looking, ignoring everything else, just looking at when B occurs. What's the probability of A occurring? This idea of conditional probabilities, it can help us understand if two events, A and B, are related. So when you kind of think through this, you can say, is the probability of one event, is it affected by the occurrence of another event? We can say that two events, A and B, they're independent if the probability of A given B equals the unconditional probability of A, or if the probability of B given A equals the unconditional probability of B. If A and B are not independent, then we say they are dependent. So we can say that, in a way, we can make conclusions about whether two events are in fact related. If they're independent, they're not related. So if the probability of A given B just equals the probability of A, you know that there's no relationship between those two. When we talk about independence, another way to think about it is it's telling us that learning about some other event, it doesn't actually tell us anything about the event of interest. So in this case, when we say the probability of A given B equals the probability of A, that's just saying you can learn all you want about B, but it's not really going to tell you anything about A. So B might be, suppose A is the event of interest, and you want to know, will I do well on the exam? And B is knowing that your roommate went to the grocery store. Now, maybe that's useful, but I think in most instances, that's not going to be very useful information. Conditioning on whether or not your roommate went to the grocery store, that's not going to tell you about the probability of doing well on an exam. So we can say that the probability of A given B equals the probability of A because B is not informative. Even after conditioning on whether or not that event occurs, we still get the probability of A. We like independent events because it's very easy to find joint probabilities. So joint probabilities, if you recall, is just the probability of A and B, two events occurring at the same time. So if we know that A and B are independent, then to find some joint probability, the probability of two events occurring, you just multiply those events together. So if A and B are independent, then the probability of A and B equals the probability of A times the probability of B. However, in practice, this is a very strong assumption. We often don't encounter independent events that can simply multiply together to find joint probabilities. Another way to think about and work with conditional probabilities in relationship to joint probabilities is to use what's called the multiplication rule. There are two variants of the multiplication rule. It's the same expression, just rewritten in a slightly different way. What the multiplication rule tells us is that the joint probability of events is given by this equation. The probability of A and B equals the probability of A given B times the probability of B. And we can also reword this, rephrase this in a slightly different way. We can say the probability of A and B equals the probability of B given A times the probability of A. We use this version of the multiplication rule to find a joint probability, the probability of A and B, given some unconditional probability and a conditional probability. So we might ask, what happens if A and B are independent? What happens when we use the multiplication rule? Recall that if A and B are independent, then condition on B doesn't matter if you're trying to find the probability of event A. So we can say the probability of A given B it just equals the probability of A. B, conditioning on that event, it doesn't tell you anything about whether or not A will occur. So let's look at what happens to this multiplication rule. The probability of A and B, as we know from the multiplication rule, equals the probability of A given B times the probability of B. But since the probability of A given B equals the probability of A, since A and B we know are independent in this case, then you can see that we can just multiply these two overall unconditional probabilities together to find that joint probability. So in a way, you can see that this idea that independent events multiply together to equal certain joint probabilities, that's really just another way of expressing this multiplication rule. We like to express the multiplication rule in a slightly different way. You can also write the multiplication rule in a format in which you're trying to find a conditional probability, and you're given a joint probability and an unconditional probability. So you can say the probability of A and B divided by the probability of B equals the probability of A given B. In a similar fashion, you can say the probability of A and B divided by the probability of A gives you the probability of B given A. So we like to use this version of the multiplication rule when we're given some joint probability and an overall or unconditional probability, and we want to find specific conditional probabilities. This is very useful because often, as we've talked about, the event of interest, the sort of quantity of interest is some conditional probability. What's the probability of having diabetes given you're overweight? What's the probability of getting a positive test result if you have breast cancer? A lot of the statements in the social sciences and humanities that we want to find out are in fact conditional statements involving conditional probabilities. So the second version of the multiplication rule, this re-expression of the multiplication rule, is often very useful for research purposes. Now, we might ask ourselves, what happens to this version of the multiplication rule if we know A and B are independent? Recall that if A and B are in fact independent, then we know that the probability of A times the probability of B equals the joint probability of A and B. To put it another way, we like independent events because the probabilities just multiply together to find joint probabilities. They're very easy to work with. So we know the conditional probability of an event is given by the probability of A given B equals the probability of A and B divided by the probability of B. But since A and B are independent events, the probability of A and B simply equals the probability of A times the probability of B. And then you can see for that last term, in the numerator and denominator, we have the probability of B. And those two terms, those just drop out. And so then we just know that the probability of A given B equals the overall probability of A. To put it another way, the knowing anything about B doesn't tell us about the probability of event A. So the probability of A given B equals the probability of A. This makes sense given that A and B are in fact independent events. Now, one warning is that you should keep track of your events. I've made this statement before, but it's important to understand that as a general rule, now it's possible, but as a general rule, in most instances, you're not going to find that the probability of A given B equals the probability of B given A. That's not going to be the case in most instances. It could happen, but usually these statements are not equivalent. To put it another way, what you're conditioning on, it's just going to matter. It's going to be important for calculating your probabilities.